Earlier in the course, we saw how to solve systems of linear differential equations using the differential operator and the technique of elimination. Now we're going to take a deeper look at solving linear systems, but using an entirely different approach. In fact, we're going to be using a matrix approach. Before I get into anything with the matrices, I just want to remind us of some of the vocabulary that we saw with linear equations, because there are parallels with linear systems, such as existence and uniqueness of solutions, the superposition principle, linear independence and dependence, and how they relate to the Wronskian, but we're going to see a different form of a Wronskian here, the idea of a fundamental set of solutions, homogeneous and non-homogeneous systems, and complementary and particular solutions, where complementary solutions relate to a homogeneous system and a particular solution exists for a system that's non-homogeneous. I said we were going to be using a matrix approach, and our first look here is going to be how we represent a system of equations in algebra as a matrix equation. We have here the system 2x plus 3y minus 5z equals 12, 7x plus 4y plus 6z equals 18, and negative 2x plus z equals negative 27. We can represent it using a matrix equation with a coefficient matrix that has rows 2, 3, negative 5, 7, 4, 6, negative 2, 0, 1, a column matrix of unknowns of x, y, z, also known as a vector, and on the right-hand side, the column of constants 12, 18, negative 27. The reason this works is because of how matrix multiplication works. Just as a quick refresher, we take the entries of the first row, 2, 3, negative 5, and multiply them each by the entries in the column x, y, and z, and end up with 2x plus 3y minus 5z. We do the same for the second row to get the second expression, 7x plus 4y plus 6z, and then the third row to get negative 2x plus z. That's the result of multiplying the two matrices on the left, and the matrix on the right is 12, 18, 27, and we have two matrices that are equal, and that'll occur if the entries in each matrix are equal, and that's how we end up with a system of equations from this matrix equation. Of course, we won't be dealing with algebraic systems, we're looking at differential equations. The systems that we're going to be looking at have the form x prime equals ax. That's the form of a homogeneous system, or x prime equals ax plus f, and this is the non-homogeneous case. Notationally, on the left, what we have is a vector, and when I write the vectors, I'm going to write them using an arrow on the top. So I would write it as x prime, but put an arrow on the top. The A is actually a coefficient matrix, much like what we just saw. And the x on the right is also a vector. Further, with the homogeneous system, the column vector f we see on the right-hand side is actually functions of t. I mean, sometimes they're constants, but they're functions of t, where t is going to be the independent variable. We'll look more into this as our examples unfold. For now, we have a system dx dt equals 4x minus 7y, and dy dt equals 5x. We know we can write what's on the right-hand side using a matrix equation based on what we just saw. The coefficient matrix has the first row 4, negative 7. The second row is 5, 0. That would be multiplied by the column matrix xy, but in this case, they're not xy the variables. They're xy functions of t, and these are the unknown functions that we're solving for. On the left-hand side, where we have dx dt and dy dt, we can write that simply as dx dt and dy dt, and in fact Leibniz notation is good here because it reminds us what the independent variable is. But this is the thing that we would represent as x prime, the column matrix or column vector of derivatives. The coefficient matrix is the one that we call A, and then the column matrix of unknown functions is the one that we're calling X. Next, we have a 3 by 3 system because we have 3 unknown functions, x, y, and z. Our equations are dx dt equals negative 3x plus 4y plus e to the negative t sine of 2t. dy dt equals 5x plus 7z plus 4e to the negative t cosine of 2t. And dz dt equals y plus 6z minus e to the negative t. The matrix on the left, x prime, is dx dt, dy dt, dz dt. That's the easy part. And then what we're going to do is we're actually going to separate out the x, y, z part from the parts that contain the independent variable t. The coefficient matrix has rows negative 3, 4, 0. Note we have x, y, and z. In that first equation, we had a negative 3x and plus 4y, but we didn't have a z term, so we're using 0 as that placeholder. 5, 9, nope, 5, 0, 9, that's where that placeholder goes. And then 0, 1, 6 times our column matrix of unknown functions x, y, and z. What to do with the expressions that include t? They get their own column. I'm going to write this column as e to the negative t sine of 2t, e to the negative 4t cosine of 2t, and negative e to the negative t. I'm going to write this as e to the negative t sine of 2t, 4e to the negative t cosine of 2t, and negative e to the negative t. Again, we have our x prime on the left equals ax plus f of t, our column vector of functions of t. Another way to write that column vector of functions, since we do see e to the negative t in every entry, we could also write this as the sine of 2t, 4 times the cosine of 2t, negative 1, and then multiply by e to the negative t on the outside of the matrix. This is scalar multiplication. I know e to the negative t is a function, but it evaluates to a real number. We would call that scalar multiplication to differentiate it from matrix multiplication here. If you need to refresh on matrix multiplication, then I encourage you to do that. Look it up. It's out there. Check out a pre-calculus college algebra book, something along those lines. Next up, we're going to go the other way. We have a system, and we're going to write it without the use of matrices. What we have is x prime equals a 3 by 3 matrix. The first row is 7, 5, negative 9, then 4, 1, 1, then 0, negative 2, 3. All that times x is equal to the column matrix 0, 2, 1 times e to the 5t minus the column matrix 8, 0, 3 times e to the negative 2t. The first things to remind ourselves are that x is equal to x, y, z, that column matrix of unknown functions, and x prime is the column, I say column matrix, it's column vector, it's interchangeable really, dx dt, dy dt, whoops, and dz dt. With that in mind, what I'd like you to do is go ahead and write down the system of 3 equations that this represents. Then come back and check it. Using that matrix multiplication, we've got dx dt equals 7x minus 5y plus 9z minus 8e to the negative 2t. And I'll pause there. As a reminder here, that was the row 7, 5, negative 9 multiplied in turn by the column x, y, and z, adding the products together. Next up, we have dy dt equals 4x plus y plus z plus 2e to the 5t. And then dz dt equals negative 2y plus 3z plus e to the 5t minus 3e to the negative 2t.